everyone, thank you so much for joining us today. Welcome to your first webinar of 2026. Well, maybe not your first webinar, but our first webinar of 2026. My name is Anya and I'm a business development manager here at KMine. Please follow us on our LinkedIn page, on our YouTube page. That's where we post all of our updates. And yeah, it's gonna be a lot today, guys. Since we're gonna take a refresh look at all of our models and bring you up to date on the core functionality that is available within our software. Before we get started, just a quick rollback about where we came from. We actually was founded in 1994 in Ukraine, and since then we extended our presence throughout Europe, Americas, which includes United States and Canada, and we grew from Ukrainian software just into international team of mining professionals, technology specialists supporting projects all around the world. So as you see today, we develop software built specifically for mining industry, supporting the entire workflow from early exploration and all the way through production. We're gonna cover all of these models today. And so you will see that our platform is actually very flexible. You can start just with one model and scale up to the full suite. Really depends on what you need, on what your project needs. And if you choose to integrate IoT or dispatch systems, you can enable real-time monitoring to keep operations running smoothly and fully coordinated. But our software was built on actually real experience that we got in our consultancy work. We have qualified persons or competent persons who prepare technical reports in line with NF43, SK1300, JOR compliant reports across project stages from mineral resource estimation and pre-feasibility study to PFS, FS, DFS, all of the FS. And we work across a wide range of hard rock commodities with a strong focus on critical minerals. So if you'd like to explore how we can support your project, please leave a comment below or reach out to us through our contact form on our website. So here's a quick overview of today's agenda. It's gonna be a lot, guys. I'm gonna tell you from the beginning, it's gonna be a long one. So grab your coffee, your tea, and get comfortable because today we're gonna cover a lot of models. We'll start with geological modeling fundamentals, moving from raw exploration data to reliable geological models. Then we'll cover block model creation, how to choose the right model for different mining scenarios. That will be followed by geostatistics, including grade estimation, variography, and resource classification. Next, we'll look at mining data import and database management, building a unified system for production and planning. And from there, we move into open pit optimization, defining the optimal final pit limit based on economical and technical constraints. We'll also review strategic mine planning, production scheduling. That includes scenario analysis and long to short-term planning. And then we'll touch on final pit design and slope stability analysis along with the drill and blast design and performance evaluation. And later we move into our underground mining which includes underground mine design and optimization. And that includes extraction blocks, ramps, stopes, and ventilation networks. So, okay, start from the beginning. All of our models, KMine offers solutions for processing exploration data and building geological models. With our database, you can manage the full workflow from importing, creating, and validating relational databases to performing statistical analysis and generating charts, identifying outliers, applying declustering and recalculating composite samples. In other words, we give you the tools to move from raw data to confident structural geological information, all within one integrated system. So in the latest release, we actually enhanced our visualization tools for displaying sampling results from mine workings and expanded functionality for quick database access. So now you can filter data, scale text, adjust key intervals parameters, all without needing to open the database itself. So this makes a data review faster, more flexible, and much more efficient in your daily workflow. Our implicit modeling functionality allows you to build surfaces and solids, model faults and vein deposits, and perform advanced mineral modeling. We use a radial basis function, specifically RBF multiquadric, combined with Marching cubes method to generate accurate geological forms. By applying interpolation functions, the system calculates values in unknown points based on known drill hole data. This allows you to define geological boundaries with precision. Using trans parameters, selected interpolators, you can model ore body limits within targeted zones. So users can choose between linear, spherical, or combined models. And for example, in a limestone deposit, you might select a spherical model with a linear drift to model calcium oxide distribution. So you can calculate variograms, define value ranges, and generate wireframe surfaces accordingly. And the system supports 3 solid creation options based on value ranges, above a threshold or below threshold. And as a result, you generate a structural set of wireframes and solids, each automatically named according to its numerical range. This numerical modeling approach is suitable for a wide variety of deposits, from polymetal porphyry systems to large ilmenite placers. And within our cross-section visualization tools, you can analyze modeling results in any direction, compare composite drill hole values to section boundaries, evaluate different iterations, and refine wireframes as new data becomes available. With K-Mine, you can also analyze the spatial interactions between wireframes, surfaces, and other objects using our enhanced custom view modes, simplifying many routine 3D modeling tasks. For example, if you imported a point cloud and need to generate a series of underground sections, you can define the number of sections and the spacing and automatically create a full set of custom views. And using the Activate Tunnel Section tool, you can control the visibility depth of object within a corridor. So all visible layers, whether point clouds, drill holes, solids, or block models, will be displayed accordingly. If you need quick access to a specific view, simply open the view table, select the required row, and navigate instantly. And you can also lock the view scale, fix the center, and adjust additional display settings. From the view list, you can quickly extract horizons or contours along sections planes, for example, from solids or block models. And with the Create Sections by View task, you define the source object and generate contour sets directly in the selected view planes. The same functionality applies to surfaces. For instance, if you have a pitch surface and you need a vertical profile along the defined line or a horizontal section at a specific elevation, you can generate it just a few steps. So available modes include view by direction, view by 3 points, view by objects, and view by azimuth. By adjusting the view range with your mouse scroll, you can visualize the pit surface at a specific depth. And with a view by objects, you can clip and isolate portions of an object behind the section plane for clearer analysis. The new fault system modeling feature allows you to quickly build framework models of faults and the entire fault systems. For example, if you have fault traces mapped at surface with a known strike and dip, you can draw them in the plan view and project them into a selected surface to assign accurate Z coordinates. With the fault system modeling task, you can automatically load a list of faults and define azimuth and dip for each one. And you can also constrain the model using an upper boundary, such as topography or another limiting surface. If no upper limit is defined, the system generates the model within the general boundaries. The sequence of faults in the table is also important. For each fault, you can define relationships with the neighboring faults and specify the interaction type. You can also automatically generate solid blocks between faults. These solids can later serve as structural boundaries for modeling veins, domains, or block models within each compartment. So if no relationships are defined, the system will divide the entire volume into 2 blocks using the first fault in the list. For example, north of the fault 1, you would see 1 solid, and south of it, another. So you can then define interactions, for instance, setting fault 2 to join fault 1 from the south. And this automatically subdivides the southern block into additional compartments. If another fault intersects the system, then you can define how it connects, whether it joins from the west, south, or another direction, and the model updates accordingly. So in the end, you generate a structured set of solid blocks that clearly represents the structural relationships within the fault system. These fault frameworks can be then used in the next stage of deposit modeling, for example, when building vein systems or structurally constrained block models. So this functionality introduces a new approach to modeling narrow vein deposits using drilling data, digital terrain models, fault framework constraints, and additional point and linear objects. It enables the creation of precise 3D surfaces for the footwall or hanging wall of each vein, and the option to combine them into solids representing integrated vein systems. The workflow also supports the use of trend parameters during surface modeling, providing a greater geological consistency and improved structural control. Although all 3D block models share the same functional fundamental structure. They all include block centroid coordinates, overall dimensions, and attribute fields. There is a significant variation in how they are constructed in the geometry of the elementary blocks. So in the current K-Mine release, we have 4 types of block models. We have cubic octree, cubic irregular with a flexible subblocking, seam irregular, seam cubic with a percentage based. So this selection depends on the initial data and the deposit type. For stratified or coal deposits, a seam model is generally the most appropriate. For vein deposits, irregular subblocking is often essential to accurately represent geometry. If the model is intended for mine planning, uniform block dimensions are typically required, and in such cases, you can use a simple octree model, a percentage-based seam cubic model, or a blocking of an irregular model to standardize block sizes. The octree cubic model uses 1/8 subblocking principle, allowing users to quickly regenerate the model with a different minimum block size. With a seam cubic model, K-Mine calculates the percentage volume of seams contained within each block. So based on these proportions, parameters such as grade, density are calculated using weighted averages. For the seam model, also known as Horizon Adaptive Rectangular Prism or HARP, the key difference is that the block height varies along the z-axis. So each block thickness is calculated based on the interpolated seam data from neighboring drill holes, allowing the model to accurately reproduce the true geometry of the seam in space. So one of the main challenges occurs in the zones with steeply dipping or overturned seams. So to address this, the latest release actually includes 2 important features: additional marker and inverted sequence. The additional marker option allows you to introduce an extra wireframe surface to correctly calculate seam thickness in steep zones, and this surface must be parallel to bedding and thicknesses interpolated perpendicular to it, ensuring more accurate block geometry. So the inverted sequence setting is used when the structural order of seams is reversed within a tectonic block, such as in folded zones, and activating this option ensures the seam sequence is modeled correctly. So we also introduced correction markers, which allows you to fine-tune seam thickness and bed base position in the most complex areas. By adding wireframe surface into the seam base, the algorithm incorporates its triangulation points directly into the block model generation process, which improves structural accuracy. For the cubic irregular block model, the functionality has been significantly expanded. So new tools such as reblocking, splitting, resizing, and merging provide much greater flexibility when working with complex models. So you can apply flexible subblocking along the X, Y, and Z axes and create blocks inside geological solids, combine them into a single model, or divide them using surfaces, and this makes modeling deposit with a complex geometry much more efficient. Also, the new release includes improved attribute visualization in section view. So block properties can now be automatically scaled according to block size with enhanced text settings for clearer and more controlled display. Also, in the latest release, we've added 2 advanced capabilities for structural complex deposits: unfolding and kriging neighborhood analysis, or KNA. Unfolding is a powerful method that virtually flattens, folded, or deforms 3D geological structures into a simplified and underformed space. So this allows for more accurate variography and resource estimation, since it normalizes variability along the geological structure rather than globally. So the workflow includes defining reference surfaces such as footwall or hanging wall and transforming the data into a smooth coordinate system. This improves interpolation for deposits characterized by bending or folding, and using the create fold geometry task, users can automatically generate a set of reference surfaces from a folded ore body solid. Within statistical analysis, unfolding can then be applied so the dataset, including drill holes and samples, is recalculated and visualized in the unfolded space. The reference surface and related data are aligned into a new structurally consistent coordinate system, such as along strike or dip. Variogram analysis and kriging interpolation are then performed within this transformed domain, revealing the true spatial continuity of the mineralization. When we compare kriging results with or without unfolding, the difference is in block grades, particularly in swath poles, and it can be significant. Unfolding makes it possible to model highly curved and structurally complex geometries where traditional methods often struggle. The latest K-Mine release introduces an essential tool for geostatistical analysis, kriging neighborhood analysis, or KNA. And after completing preliminary statistical analysis, building anisotropy maps, and defining variogram models along the three axes of the search ellipsoid, users then can proceed directly to KNA. During the discretization estimation, you can either select an existing block model or define virtual block dimensions along X, Y, or Z axis, and each block is then subdivided into a specified number of cells for testing. The key optimization criteria are conditional bias indicators, including slope of regression and kriging efficiency. Once optimal discretization is determined, then the workflow moves to block size optimization. Multiple block size scenarios can be tested and compared to select the most appropriate option. The next step is defining the optimal numbers of samples and managing negative weights, as these directly impact conditional bias and estimation quality. K-Mine supports multiple kriging methods, including simple kriging, ordinary kriging, kriging with external drift, and co-kriging. KNA helps determine how many samples to use, their optimal search distance, and how they should be weighted. The final result is a set of optimized kriging parameters, ensuring accurate, unbiased, and geologically realistic block model estimates. At the same time, it's important to remember that while many software packages now offer a wide range of block model types, the choice should always depend on the model purpose. So highly sub-blocked or complex models are not always suitable for mine planning and pit optimization. So in such cases, you might just need to transform the model into a regular format, applying a comprehensive and practical decision-making approach. All right. Now let's take a look at the planning process and how it's structured at K-Mine and what tasks it covers and how it works from a user perspective. So the core principle is everything is one environment, right? So no switching between applications, no interruptions in workflow, and this allows smooth navigation across planning stages and models. Strategic planning begins with optimal pit boundaries model. Its main objective is to define the optimal pit shell, and the engine is based on the classic Lorentz-Grossman algorithm, but optimized for model performance, enhanced with advanced metrics, and capable of processing large block models within minutes. Beyond pit optimization, the model supports sensitivity analysis, project shell evaluation, pushback generation, and the creation of base mine schedule. The next levels, which is long-term and short-term planning, are managed within the scheduling model. While the data inputs in methodologies differ, the goal remains the same, which is defining the optimal extraction sequence for each planning period. So at the operational level, planning integrates with dispatch systems inside K-Mine, so the implementation may require initial configuration, but it results in a fully connected, coordinated production workflow. So when we actually ask if we have integration with dispatch of fleet management systems or IoT devices, we always say yes, obviously, but it also makes sense for you if you use mine planning or pit optimization tool, because that's where kind of like it's worth the investment. So for clarity, let's briefly review the conceptual framework of mine planning. Strategic planning represents a major part of the cycle because it establishes the foundation of all subsequent technical and financial decisions. The optimization model works closely with the design model, so together they define the optimal pit shell and generate pushbacks and prepare the project for the next stage. From there, the scheduling model develops the extraction sequence, which is then followed by design refinement and financial analysis. In practice, three core models cover the full mine planning cycle, from identifying the optimal pit limits to evaluating the project's financial attractiveness. So transitions between stages are seamless and operating as a single integrated workflow within a clear environment. So now let's take a closer look at the first model, which is pit optimization. It's the first model in the planning chain, okay? So it's a step-by-step workflow, makes strategic planning clear and transparent, even for complex projects. You can see on the screen all of the things that it can do, from the generation of multiple scenarios of pit development and cash flow analysis to comparison of scenarios, creating pushbacks and schedules. Optimization results are also presented in multiple formats, allowing you to quickly understand the level of optimality at a glance. So within a single model, you can define the optimal pit shells, generate development phases, identify key profitability drivers, and evaluate project scenarios and build the initial extraction sequence. So let's walk through the project creation process, briefly focusing on the key steps. First, we begin with the block model and topographic surface. So the block model is constrained by topography, added to the project, and configured to separate ore from waste, establishing the foundation of optimization. Then we define the overall slope angles. This is the critical stage, as it establishes interblock relationships used throughout the entire block. And K-Mine offers three approaches: by vector, by geotechnical wireframes, and by block model attributes. And after a calculation, the system highlights the largest deviation from design parameters and their exact locations, which allows you to immediately review it. We then move to economic parameters. Revenue factors are defined first, as they directly influence optimization outcomes. Exclusion zones can also be specified, which are areas the algorithm must completely avoid. Then the economic modeling stage comes, and the final product management, final product parameters are defined, and dependency formulas can also be applied to individual metrics for greater accuracy, and additional post-production costs may also be incorporated. Processing costs can also be defined using a regression-based formula, a regression equation developed in Excel and can be transferred directly into K-Mine formula editor, linking ore quality to processing cost. And this empirical relationship improves evaluation accuracy and helps identify the most promising zones. Finally, we define the cutoff grade and recovery factor, and we recommend to apply the formula-based logic here, as these parameters significantly impact profitability and NPV, particularly during sensitivity analysis. So next, we define mining costs, including dilution and the ore loss parameters. Then we set haulage costs with an option to link them directly to pit depth for more realistic modeling. Capital expenditures can also be assigned, reflecting investment required to develop specific zones. Some costs may not influence the optimization algorithm itself, but they are included in the final economic summary. So we completed the setup by defining NPV parameters and life of mine settings, and the project is saved. Then the system moves to results. So this is the key outcome, the optimization results, right? What often requires significantly more time in other software generated here in a structured, very transparent format. Block groups are clearly show how pit size changes with variation in final product price, supporting informed decision making. And the results can also be reviewed through charts like tables. They offer multiple display modes, which each providing a different analytical perspective. And you can select the appropriate revenue factors. And it's actually critical. The system provides comprehensive data set along with the guidance to support an optimal decision. So Let's return to the table and focus on APV metrics. It provides a clear indicators of long-term project attractiveness. Identifying the revenue factor with the highest MPV is straightforward. However, it's important to review the other metrics as well. They often provide critical context and support a more balanced decision. The output of strategic planning is a wireframe generated from the selected revenue factor. This becomes the foundation for the next planning stages and represents the key objective at this step. The logic behind defining the optimal pit shell is clear and structured, and once the required input data is properly configured at each stage, it just becomes clear. So then we move to supporting strategic tools, including pushback generation. The automatic method generates phases based on defined parameters, while the manual method allows full control over geometry. In practice, the most effective workflow to begin is to begin with automated generation and then apply manually refinement using guidelines to achieve the desired result. So we add polylines to the project, run the calculation, and review the results from the different perspectives. Once the geometry is confirmed, we export the wireframes and move to the design stage, including development of the whole road network, concept, and related elements. Scheduling with the optimization model is based on block groups created at the intersection of benches and the optimal pit shell. After setting the target parameters, the system generates wireframes, block groups, tables, and assigns blocks to periods directly within the model. Next, the sensitivity analysis. This is not a forecast. It's a series of full recalculations with each scenario evaluated independently. So the results clearly show how variations in individual parameters impact profit and MPV, helping identify the most influential drivers. We also have additional tools for evaluating the ultimate pit shell and the alternative design options. These are typically applied after the detailed pit design has been completed. So now we move to the model responsible for design tasks, including pits, infrastructure, and various engineering structures. This is the one of the core K-mine models, because the foundation on which the system was originally built. It includes a wide range of tools designed to simplify and accelerate routine engineering work. This model allows you to work either with individual elements or generate large-scale designs, such as ultimate pit shells or waste dumps, within a single automated workflow that accounts for multiple parameters. At the same time, the manual approach remains precise and flexible, so each element can be created independently, offering full control and detailed customization when needed. So you can see the key elements handled with the manual design approach, which are fundamental and yet critically important components of pit engineering. This includes crest and berm construction, haul roads and ramps, wireframe creation, volume calculation, cross-section generation, and more. These tools support projects at any scale and complexity, providing precise control over every design element. The automated approach, though, often draws the most attention, and for good reason. It stands out for its simplicity and versatility, and the plugin supports pit design from top bottom or bottom top, as well as waste dump design, with a broad range of settings to significantly reduce design time. As a result, you get a clear and structured optimal pit design in just minutes, and even more complex configurations can be completed under an hour. So the dynamic design plugin supports construction from multiple lines at different elevations or from a single line combined with a bench list. Before starting, it's important to review the work area from multiple perspective and define the core design concept. If an optimal pit wireframe is available, it can be used as the base for generating contour lines by elevation. All you need is a list of benches, which can be created in semi-automatic mode. And once generated, contour lines can be smoothed to define parameters with a single action and added to the bench list. All lines are stored within the project and can be adjusted, replaced, or removed at any time. We had the first haul road, and initial iterations may be approximate. Refinement of all becomes more precise as geometry develops. Once the road layout concept is defined, modifications are instant. You can add switchback, widen or narrow the road, terminate its development, merge multiple roads, all supporting flexible design control. The number of roads is unlimited, so you just need to maintain logical connectivity between pit areas and ensure optimal access from the surface. For a quick project assessment, we simply add the topography, select the block models, and calculate volumes. For verification, we can display the exact portion of the block models involved in the project, and this gives us immediate visual control. The construction results are available in several formats: project wireframe, solid, resultant wireframe, and project lines. So you can choose the format that best fits for your workflow. Because everything operates in a unified environment, tools from other models such as cross-section or element comparison are always accessible. So the resultant wireframe combines the design with the actual state presented in a consolidated wireframe format for clearer evaluation. We've also introduced a low boundary constraint wireframe. This is particularly effective for tabular deposits, eliminating the need for manual pit floor trimming. Waste dump design, whether interim or final, requires only a single base contour to define the geometry. The principle is similar to pit design, but with an upward tapering geometry. We add whole rows and constrain top tier as required, depending on the project parameters. For topography, we simply select the pit design result, and this allows both projects to be combined into a single integrated model. In just a few minutes, we generate both the ultimate pit and the waste dump designs consolidated within one wireframe environment. The workflow is structured, efficient, and pretty straightforward, if you ask me, and resulting in returning to the optimization project, it will allow us to review additional capabilities. For project shell evaluation, we select the required wireframe in the layer editor, and the analysis is ready to proceed. We review the key metrics, so similar to those used in optimal pit analysis, and compare the results side by side. This leads to a clear decision. Okay, does the design meet expectations, or does it require refinement? The design results can be compared directly with optimization calculations. We select the relevant revenue factors and project variance, and all data is consolidated into a single table or chart. So multiple scenarios, 5, 10 or more, can be evaluated simultaneously to identify the most profitable option. For more focused analysis, we compare only the target shell and the achieved shell. This gives you a tool that doesn't just simplify your work, it generally helps to determine the optimal pit. So we've already covered strategic planning and pit design. Now let's move to the scheduling component, how it is organized within our environment. So the scheduling model covers all stages of open pit mine scheduling. The difference lies only in the parameters and approaches used to reach the objective. Working with pushbacks supports long and medium-term schedules. Building on previous scheduling results allows transition into short-term planning. And the primary goal of the model is to define the optimal extraction sequence while meeting the target constraints. It also calculates haulage distances by periods. So then, underlying principle is to minimize TKM, ton kilometers metric. So let's review the different approaches that are available in the scheduling model. We'll begin with a short overview and then move into a more practical example. So the first and most widely used approach for long-term and medium-term planning is the automated solution search. It is designed to achieve defined target metrics while strictly respecting operational constraints. The second approach is based on excavators and events. Each piece of loading equipment follows a defined event sequence, and that sequence determines the extraction order. Planning is performed through a direct manual control of the fleet. So the third approach also uses excavators, but without assigning them physically to specific areas. Instead, one unit is allocated per area. The mining intensity in each area is adjusted, and this defines the extraction volumes for each period. And these methods are not mutually exclusive. They can be combined to achieve the most effective scheduling result. So every mine planning engineer is looking for the right tool to meet the project demands. And in this section, we'll review the scheduling approaches that are available in K-Mine. So there are three distinct approaches built around two main directions, automatic and manual scheduling. Within the manual direction, we'll look at two structural methods for achieving planning objectives. The first step is setting up a project in the scheduling model. So import the block model, define mine areas, and specify how they will be mined. Clarify your objectives. For long-term and medium-term planning, the automatic solution search is typically the most efficient option. So just define your target parameters, then the system determines when, how much, and what material should be extracted to meet those goals. Targets can be grouped and prioritized, and mining sequences can also be adjusted manually within the automated workflow. The results are presented as block sets by planning period. For each interval, you can review the remaining rock mass and adjust priorities for the next stage. Each period, individually or combined, can be visualized through charts or diagrams. And charts simplify show interpretation of planning results, and output may also include wireframes or polylines for each planning period. And this approach is particularly effective for long and medium-term planning based on target parameters. So the next approach is applicable across all planning horizons. Its focus is defining when and how much material is extracted from each mining area. You work with extraction units, so representations of mining intensity per area. Intensity is adjusted manually through events. You define required productivity levels for each area over a specific period of time, and then evaluate performance using diagrams. If ore production is insufficient, then just increase intensity where capacity exists. If additional waste removal is required, then you just activate a new mining area. For a more complete planning picture, you can integrate haulage routes. When transportation is included, you should always configure material receiving points and their requirements. This significantly increases the level of detail in reporting, and the results are presented in tables covering the deposit development across all planning periods. Of course, data is broken down by excavator, by mining area, by bench, and by interval. So transportation reports include loading points, dumping points, material types, and route categories. And in the end of the transportation report, you'll get a summary for each period, including all haulage elements. Each calculation period generates its own unique block set. It reflects the specific mining conditions of that interval and can be displayed independently. All results can be exported as wireframes and polylines. So the third approach is the most detailed. It is the best suited for short-term planning and in some cases medium-term planning as well. The concept is pretty straightforward. So you position real excavators with actual equipment count and productivity across the pit. You define all potential working locations. Through excavator events, you establish the sequence of equipment movement as areas are mined. As with the previous method, the haulage network can be integrated for more granular planning results. So the resulting mining sequence will differ from earlier approaches because the extraction intensity has been adjusted across areas. The pre-configured chart tabs provide clear visualization of the planning concept, and graphs make comparison easier than tables alone. You can export the results to Excel for deeper analysis, but charts clearly show whether targets have been achieved. If you need to adjust something, you can just modify equipment allocation and the impact evaluated immediately. So this approach supports development of both long-term strategic plans and short-term operational schedules. The three approaches presented here are a foundation. So there are no strict limits. Everything depends on your strategy. So you need to define your scheduling paths, build alternative plans, compare them, and select the optimal one. So now let's move to our next model, which is the stability analysis. The stability analysis is designed for geomechanical assessment of slopes, pit walls, benches, and waste dumps throughout the mine life cycle. It combines classical limit equilibrium methods with advanced numerical approaches, including finite element analysis, supporting reliable and informed engineering decisions. So engineers can work directly with geological cross-sections, heterogeneous rock masses, groundwater conditions, and external loads. The model provides both quantitative factor of safety results and visual insights into stress distribution, deformation, and potential failure mechanism. This makes it a practical tool for slope design validation, risk assessment, and design adjustment in complex geological conditions. So you can see on the video an example that demonstrates open pit slope stability analysis using the Hochbrunn failure criterion and the strength reduction method. The analysis is based on defined rock materials characterized by physical and mechanical properties, including Young modulus, Poisson ratio, unit weight, GSI, and related parameters. A vertical pit cross-section is generally generated directly from the model. Rock boundaries are represented by surfaces and accurately reflecting the geological structure of the slope. So here's what's happening. Material assignments are linked between the cross-sections and rock property lists. Boundary conditions are defined. Numerical parameters, including calculation mesh, iterations, and accuracy, are then configured. Once the setup is completed, the numerical simulation then is launched using the strength reduction approach, and the output includes the factor of safety. So in addition, displacement maps and stress distribution maps are generated and complete with legends for interpretation. You get a tabular report as well in the end, and you can export it in standard formats or use it for further analysis and chart generation. On the next video, you'll see an example that demonstrates slope stability analysis using a limit equilibrium approach with the force polygon method. The calculate pit wall stability task is applied in surface mine control, and this task supports slope stability assessment and rock mass deformation analysis using open pit operations. Limit equilibrium methods are used to identify potential slip surfaces and calculate the factor of safety based on force and moment balance. In this case, stabilizing and driving forces are evaluated using the force polygon methods and applying vector equilibrium within a homogeneous rock mass. There are additional limit equilibrium methods that are also available and can be applied depending on the project requirements. Input data includes rock mass strength parameters, physical properties, digital terrain models, and defined calculation boundaries. To establish the calculation zones, the two supporting boundary polylines are created perpendicular to the bench crest. This method supports analysis of scenarios where sliding occurs along weakness surfaces, such as faults, and allows inclusion of groundwater conditions. Results are include the calculated factor of safety and defined failure prism. So you can add these outputs directly into the report and export it in usual formats, including PDF. So let's check out the next task, which is the calculate stability of heterogeneous wall task. It is designed for analyzing pit wall stability under complex geological conditions where rock mass heterogeneity plays a critical role. It supports engineering decisions focused on slope stability and operational safety and reliable mine performance. The analysis is based on classical limit equilibrium methods using Bishop simplified, jumbo, or force polygon. These methods allow flexible evaluation of different stability scenarios and provide a reliable factor of safety estimates. Depending on geological structure and selected strength models, the workflow begins with creating an engineered geological cross-section in the area of interest. In this example, the section passes through an internal waste dump, but the approach applies to any pit wall. Geological units are defined on the section and assigned geotechnical properties using the built-in material database. Both Mohr or Hochbrunn strength criteria are supported here. So to reflect geological complexity, you can introduce a weak layer to represent potential failure surfaces. A groundwater table can also be defined to account for pore pressure effects. Surface loads are configured separately, and this may include static or dynamic loads such as equipment, stockpiles, or infrastructure. Once all parameters are defined, you see the calculation is performed. In the result, you get a factor of safety, the potential failure wage, or a load distribution output for engineering evaluation. All right, let's move on to our next model, which is the drilling blast design model. It is intended for engineering planning and design of drilling and blasting operations in the open pit mining. It provides tools to create and manage drill patterns, define hole geometry, and calculating explosive charge distribution based on bench and face geometry. The model supports key blasting parameters, including powder factor, initiation sequence, and timing. All of these allow engineers to control fragmentation quality, energy distribution, and overall operation safety. All designs remain directly linked to the mine geometry. This ensures fast and consistent updates whenever bench geometry or design parameters change. So let's walk through a practical example. We'll begin with the training model. The first step is selecting the area for the blast block design. We created using the create drilling project task. And in this example, initialization is based on 3 bench edges, crest toe and all toe. This ensures the block geometry is defined correctly, accounting for both the upper and lower boundaries of the rock mass. For the all-toe parameter, we enter a value of 25 meters. This preserves the whole road berm and maintains proper pit slope formation. Next, we click Create Project Area, and the system displays the area where the blast holes will be generated. We then create the drill holes, and at this stage, the blast block is already formed. For clarity, we turn off the project criteria and the wireframe and switch to top view and select the block. Now we open the Create Wiring Up Lines task, and the form appears. The first step is initializing the drill and blast block. We select the blast holes and use type by selected to initialize them. Next, we move to changeable object section, and here we define which blast hole properties will be used during the wiring process. In this case, we specify the layer for strong blast holes, and we define that delay timing will be calculated using a formula. We select the delay algorithm based on shock tubes, and we assign an in-hole delay of 500 milliseconds. This standardizes hole behavior while controlling the detonation sequence through surface wiring, and we then proceed to the wiring setup. We see a visual representation of the initiation schemes, and that is appearing. Here we define delays for the wiring lines, and in this project, wiring up lines connect hole to hole. So joining blast hole pair serves as the main trunk line for initiation the entire block. The operation drop-downs includes 5 wiring scenarios, and we select one of the most commonly used configurations. After selecting the operation, we draw a line defining the base wiring trajectory. We select it, click Apply, and wire the block from the main trunk line towards the periphery. And the dynamic tools allow further refinement, so you can adjust line width or inclination angle, and it's particularly useful for blast blocks with a complex geometry. So on the screen, we can clearly see that the main trunk line displayed in black, interhole shock tubes are shown in red, and arrows indicating the detonation directions and delay values displayed in brackets. Once wiring is complete, we close the form and switch to the blast simulation tab. The first step is selecting the initiating chord object and opening the display settings. In the graph group, we enable the required options, so wiring up line, fly rock, breaking line, blast hole detonation, detonation graph, and hillside. This allows visualize not only the detonation sequence, but also the rock breakage process. So below that, in the construction settings section, we configure the blast impact zone and safety zone, and we can define objects that must be excluded from the blast influence area. If equipment, structures, and other critical elements fall within the hazardous zone, the system automatically issues a warning. This allows you to adjust parameter or object relocation at the design stage. Next, we move to the settings tab. If in construction object group, we enable visualization for detonation delays, which is calculated and displayed after calculation, damage zones, and breaking lines showing expected rock movement. Visualization intervals are defined numerically, and the default value is 50, but it can be adjusted as needed. We click apply, and the system recalculates delays from the first to the last blast holes. And now we switch to the simulation tab and launch the dynamic blast simulation. The initial run is performed in real time. So playback speed can be reduced, for example, to 0.5 to review each stage in detail. So the simulation can be also paused in any moment, and we then enable the number option in the maximum charge group. So you will see a graph at the bottom of the screen showing delay values from minimum to maximum across in the block. Using this graph, we can identify which holes detonate at 900 milliseconds and systematically verify the entire initiation scheme. So you can see that our drill and blast model supports not only blast block design, but also detailed pre-blast analysis completed before field implementation. Now let's check out our grain size analysis model, and it is used to evaluate rock fragmentation after blasting, so based on image data. The model automatically detects and measures rock fragments using photographs and survey imagery, and first will load the source image, and then comes image calibration and spatial referencing. So this ensures fragment sizes are calculated in real scale and can be reliably compared across different blasts and locations. So then the area of interest is defined by outlining the calculation boundary. Once the analysis is launched, the interface displays two synchronized views. So the original image on the left and the processed image on the right, showing detected fragment contours and applied filters. Accuracy depends on proper adjustments of processing parameters, including brightness, contrast, boundary sensitivity, minimum fragment size, density, and shadow and direction. And these settings are refined to achieve precise detection of individual fragments. An optimal result is achieved when contours clearly define the maximum number of district fragments without excessive noise or over segmentation. So once the calculation is complete, results can be stored and linked to a database. You will get the report automatically, which will include statistical summaries and the grain size distribution histogram, and the output table will show key indicators such as size ranges, fragment count, minimal and maximum values, average fragment size, and percentage of oversized material. Okay, so next we're moving towards the surveying model, which provides a unified environment for processing, managing, and analyzing geodetic data in both open pit and underground operations. It supports the full surveying workflow from field data import and network adjustment to surface modeling, volume calculations, and monitoring of mine development. So the model ensures accurate control of coordinated networks, creation and updating of digital terrain models, and detailed mapping of surface pit and underground workings. The surveying results are directly integrated with the design, geology, and planning models, and this ensures full consistency of spatial data across all stages of mine planning and operations. So as a result, the surveying model becomes a core tool for maintaining reliable spatial control, supporting production measurements, and ensuring data integrity throughout the entire mine life cycle. So now we will show you how surveying data is stored, managed, and updated within the surveying database. So the workflow begins by opening the surveying database, which is a centralized repository for all survey records, and every entry contains detailed information including survey date, log record, instrument type, measurement accuracy, surveying name, and the original source file. The structure ensures full traceability and consistent data management. Next, the survey record is selected and visualized in the project workspace, and in this case, the survey represents a newly drilled blast block where color coordinates were measured. Once loaded, key geometric parameters such as burden and spacing can be calculated and reviewed, and you can display additional parameter if you need and prepare the results for reporting or printing. The workflow then returns to the database and to select another survey entry, and this database reflects the updated position of the pit crest after blasting. So to update the digital terrain model, and the reshape line tool is applied, and the previous crest line is smoothly adjusted to the new surveyed position, updating the geometry of the mining front. Finally, the surface framework is rebuilt, and as a result, you get an updated digital model that accurately reflects the current state of mining operations. The next example, we will show you several approaches to volume calculation and surface mining based on updated surveying data. So the workflow continues from the previous steps, where the updated pit surface framework has already been created, and at this stage a solid representing a mine block and is added to the project. This solid reflects the volume between the previous and updated pit surfaces after excavation. To calculate the volume, we select the solid and launch the calculate volume task. This system automatically normalizes the geometry and computes the volume. You will see the results in the structure table, and this method can be applied to a single solid or multiple solids simultaneously, supporting batch volume calculations. In addition to solid-based methods, the model supports alternative approaches, which is one option is the vertical section method, where volumes are calculated using a series of cross-sections, and another approach calculates volumes between two surface frameworks, allowing simultaneous evaluation of excavation and fill. So if a block model is included, the system can also calculate tonnage and quality parameters for the material within the measured volume. For more precise analysis, the calculation area can be limited using user-defined boundary. After selecting both surface states and applying the calculation, the system generates the summary table, and this includes excavation volume, fill volume, tonnage, and optional quality indicators, which are ready for further analysis and reporting. The calculate blockout and developed ore volume function is designed for mining surveyors and planning engineers who need precise evaluation of developed ore, blocked out ore, and waste within an open pit. This tool supports level-based calculations and accounts for complex pit geometry, including ramps, slopes, and excavation contours, providing a reliable basis for production control and technical reporting. The workflow begins with defining the input data. So the user selects layers containing crest and toe boundaries with the option to include or exclude ramp geometry. These elements must be correctly structured to ensure accurate volume calculation. At the same time, layers representing ore body projections onto the working pit surface are also selected, and these are typically defined as 3D surfaces corresponding to ore zones. The interface allows fast selection of required layers and sub-layers, and you can filter objects such as crests, toes, or ramps, and additional calculation parameters can also be defined depending on the production task. These includes slope angles, distances from the toe to the boundaries of developed and blockout ore, and options to include or exclude bottom areas when generating wireframes. For mass calculations, density values for ore or waste can also be specified. You can also apply optional scaling coefficients, particularly useful for large and heterogeneous data sets. Once the calculation is complete, the system generates a detailed results table, and the output includes volumes and weights of developed and blockout ore, waste volumes and weights, ramp-related quantities, and additional indicators such as total cut length and mine cut length provide insight into operational efficiency. You also get a 3D visualization of ore and waste distribution, and all this support and accurate reserve tracking reduces manual effort and improves decision-making throughout ongoing mine development. All right, so let's move on slowly to underground mining, which K-Mine can also handle in surveying. In KMine, this functionality can also be managed through the Open Studies database. It is used for processing surveying data in both open pit and underground operations, and the database provides a centralized environment for managing field measurements and automated routine surveying tasks. It supports data imported from major instrument manufacturers, including Topcon, Leica, Trimble, Soke, and others. Once data is imported, the site is divided into working levels, which would allow the surveyor to focus on specific areas. And in this example, single level is selected for analysis, and to evaluate material movement, we use the task calculate wireframe volume. It computes the volume difference across the selected level, and it also supports simultaneous calculation for multiple wireframes, enabling efficient comparisons between survey states. In our case, 2 wireframes are selected, and you can see the resulting volume right away in a structured result table. So next we use a cross-section tool through the working area, and section lines are drawn, and we select a predefined template. We set the output mode to 2D or 3D and define the result location. The generated cross-section shows only minor deviation in the zone. However, when a longitudinal section is created along the working direction, more significant differences become visible. This provides additional insight into excavation processes and surface changes. So diving further into underground mining, let's talk about stope optimization. It is designed for engineering level optimization of underground stopes, and its objective to maximize ore recovery while controlling dilution and maintaining strong economic performance. This model operates on a block model-based evaluation, so it identifies economically viable stoping volumes under defined geological, geometrical, and operational constraints. So the model supports different deposit types and mining methods. Engineers can configure stopes, shapes, dimensions, and economic criteria, including cutoff grade, value, and tonnage. You can generate and compare multiple optimization scenarios. Optimized stopes are visualized directly in 3D, and they can be exported for further underground planning, scheduling, and design validation. This makes the model a practical bridge between the geological model and the mine planning workflow. You can use this model if you need to determine optimal underground stope boundaries with the objective of maximizing ore recovery while controlling dilution and economic performance. First, you load a geological block model and then select the target qualitative parameters. The technological constraints like deep angles, cluster spacing, and stope geometry are defined based on the selected mining method. A built-in shape editor allows flexible customization of stope profiles, ensuring compliance with both mining and safety requirements. So next, we should configure the economic component of the scenario. The user selects the optimization method and defines the calculation and calculates the cutoff grade and adjusts clusters quantity factors and sets key economic parameters. In this example, grade-based optimization is applied using a fixed iron cutoff grade of 53%. An important step is to define limiting wall angles. So these parameters directly affect stope flexibility and are determined by mining technology and rock mass stability conditions. Dilution and ore loss are also incorporated into optimization process, and you have multiple options to ensure accurate volume estimation and alignment with the selected mining method. Once the calculation is complete, you will see the results as dedicated layers. Each block is displayed in random colors for visualization processes, but the optimized stopes can be used directly for underground design, scheduling, and production planning. But how do we determine which scenario performs better under real mining conditions? So let's walk through the process of comparing multiple stope optimization scenario and see how the KMine model supports informed engineering decisions. So first, let's set up the first optimization scenario. Connect the block model containing ore grade data. Then select the target valuable valuable component, define the stop geometry, and next we'll specify key parameters, cluster spacing, deep angle, and the optimization method. In this example, we apply a grade-based approach with a minimum cutoff grade of 53% iron, and then we define sidewall constraints, including maximum wall angles and allowable shifts. We also introduce dilution and ore loss parameters to reflect realistic mining conditions. And we run the calculation, and you'll see the results in the results table. Now, let's create the second scenario. We adjust selected economic and geometrical parameters and recalculate and evaluate how these changes affect recoverable volumes and grade. For the third scenario, we modify the cutoff grade, dilution, and loss parameters, and we can use this step to assess sensitivity to technological constraints. So after calculating all scenarios, let's compare the results. For that, we use sorting and grouping tools and the comparative bar chart. So the chart clearly highlights differences in mining volumes, grades, and losses and dilution. If you need to, you can export the chart and include it directly into technical reports for further analysis. So moving on to our underground design model, you'll see that it provides a parametric environment for creating and validating underground mine development geometry. You can use it to design levels, ramps, drifts, crosscuts, raises, and stop boundaries with full control over geometric parameters and engineering constraints. All development elements are created in 3D and directly linked to geological models, block models, and stop optimization results. This ensures spatial and technical consistency throughout the planning process. So the model includes tools for constraint-based design, clash detection, volume, and tonnage calculation, design validation, and the workflow helps you to evaluate alternative layouts, verify design feasibility, and prepare accurate engineering data for further schedule and ventilation and operational planning. So let's see how it works. We start with the excavation network design feature, and this tool allows you to quickly create a project for horizontal underground workings at selected levels. The initial data comes from the stopping blocks that were previously generated in stop optimization. Now we start by selecting the levels we want to work with. In this example, you can see that there are 3 levels visible, but you can select all levels or just one. Next, we define the access point, in other words, the shaft. The system can automatically determine its location, but if a shaft already exists, it just simply specifies its position manually. Then we move to defining excavation direction, and we click on excavation direction button. The algorithm proposes several options. In the most cases, the appropriate direction appears among the very first few suggestions. After that, we adjust the project accordingly, according to the select mining system and equipment, and you can also adjust offsets, define conditions for splitting and merging workings, and set entry angles. You can fine-tune additional parameters, and this ensures the project aligns precisely with your operational requirements. These elements were generated automatically based on the results of stop optimization and form the basis for designing ramps between levels. So first you design the entry point of the level, as well as the direction of the future ramp, and you can do it directly in the workspace using snapping tools or through the parameter table. Then you start designing the ramp design using segments. Each segment can be straight or curved or completed using snap to point function. For every segment, you have key parameters, including azimuth, radius, gradient in degrees, percentage, or per mile, and length, turning direction. A key feature of this tool is the dynamic mode, though. Any modification, such as changing the radius, for example, of curved segment, or adjusting the gradient, automatically recalculates the entire ramp geometry, including all subsequent segments. This allows quick testing of different configurations while respecting gradient limits and ore body geometry. In this example, we create straight segments, add curved segment, and complete the ramp by snapping to the lower level. So after clicking apply, the system generates a complete tunnel with a specified profile, and in this case, an arch section measuring 4 by 3 meters. If you need any additional development, you don't need to restart the task. Most parameters remain valid, so allowing new entry point to be defined and the dynamic mode to be reused. So finally, you can see that the tunnel solid is generated and connected to the rest of underground infrastructure, making the updated layout immediately available for further design and analysis. So now let's take a look at the drilling and blasting design feature, which also a part of underground design model. The drilling task combines setup tools, dynamic interaction with objects, and flexible view management to support efficient drill pattern design. This workflow is divided in 2 stages. First, we configure the input parameters, defining the main constraints and drilling settings. Then we execute the task, and the result is generated automatically. And in the beginning, we select the drilling stations and launch the task, and you get the result almost instantly. So you see the generated drill fans appear in the workspace. And in the table, the results are organized by horizons, making review and management straightforward. For more efficient interaction, we can use view management tools and just select an object from the list to activate it in the workspace. And all newly created objects are automatically stored in the corresponding layers. One key feature is the ability to dynamically adjust drilling block boundaries, and basically when the block geometry changes, the drill fan recalculates in real time. And this helps to evaluate immediately alternative configurations. Just with a single click, display or hide key drilling parameters such as angles and numbering, and you can also add and remove drill holes, block individual holes, adjust the length, and split a fan into separate groups. Additionally, if you need to, you can configure each drill fan independently, which helps to adapt to complex geological conditions, including deflection drilling scenarios. So with the K-Mine underground design model, you can work simultaneously with the multiple data types, including design geometry, surveying data, and geological information. And this integration maintains consistently between mine design and geological interpretations throughout the planning process. In this example, we use a block model containing geological and grade information as the primary data source. So the system provides tools to visualize, filter, and analyze both qualitative and quantitative parameters. So to focus on a specific mining area, you intersect the block model with the solid representing the design stope. And this operation isolates not only blocks located within the stope boundaries, creating a direct link between a geological model and the planned extraction geometry. Once separated by the stope solid, we activate the dedicated analysis task, and you can use these tools to evaluate or volume, tonnage, and grade distribution within the selected stope. So as a result, you calculate stope reserves directly from the geological block model and the actual design geometry. This all provides a reliable foundation for reserve estimation, further mine planning, and validation of underground design decisions. So this entire workflow includes 2 related tasks that is used to estimate the quantitative quantities of materials required for underground support system. The process is based on support passports. So they define the support type, the geometry of mine working, and the composition of a single support set. So you can create passport directly within the system, or you can load them from the existing templates. So this allows standardized support configurations to be reused across multiple workings. And once you define support passport, you should assign it to selected underground workings such as crosscuts or drifts. This way, you are created a direct link between working geometry and the selected support scheme. And once you do that, run the support material calculation task. The system calculates the total number of required support sets and determines material quantities and tonnage for all support elements. If multiple workings are included, then the system automatically aggregates results into a consolidated summary. And as usual, you can export the calculated data in standard formats and use it directly for material planning, cost estimation, and preparation of technical documentation. So now we have a few other models that I want to highlight, and especially when we talk about underground mining, it's important to discuss ventilation system. So our ventilation model is designed for engineering level planning and analysis of underground mining ventilation systems. You can use it to define ventilation networks based on actual mine geometry using drifts, raises, and shafts, and to model airflow behavior throughout the mine. Here you can configure fans, regulators, control elements in detail, and you can also calculate airflow distribution, pressure losses, and overall network balance. The model also provides tools to analyze gas and contaminant distribution and to evaluate the impact of different ventilation scenarios. So let's see briefly how to set up and calculate a ventilation network in K-Mine, from initial data import to analysis of aerodynamic parameters. The workflow begins with importing the ventilation layout from a DXF file. At first, the network appears as line work, then we'll convert it into excavation objects, and this allows you to assign geometry, attributes, and physical properties to each mine working based on available technical data. And then we build the network topology by defining nodes. This ensures correct connectivity between workings, and at this stage we define collection panels, ventilation raises, intake and exhaust airways, and service workings. So we also add the flexible ventilation ducts for dead-end workings to complete the network. Once the geometry is ready, we calculate aerodynamic resistance for each working. So the system considers length, cross-section, resistance coefficients, and additional aerodynamic elements. And after calculating resistance, we add a fan to the network. Using fan performance data, K-Mine evaluates operating mode and calculates airflow distribution throughout the mine. Dynamic airflow labels appear for each working, allowing quick verification against the ventilation requirements. In this specific example, the initial fan configuration does not provide sufficient airflow in several dead-end workings. So we select a more powerful fan and recalculate. And now airflow increases across the network, and we can evaluate compliance with the ventilation design criteria. Now let's take a look at how you can manage airflow distribution within the ventilation network. You can do this by using ventilation doors, and for each door we define the required aerodynamic resistance, and then we install doors on selected workings so we can restrict airflow in certain direction and increase it in others. So as a result, for example, airflow in working number 10 reaches 74 cubic meters per second, and at the same time we meet the regulatory airflow requirements in the dead-end workings. So you can see that all key aerodynamic parameters are consolidated in the calculate ventilation system task. Here you can review air consumption, airspeed, dynamic resistance, and additional resistance, depression, and other indicators for each working. And of course, if you need to, you can export the results in Excel and use them directly in the project or reporting documentation. Finally, the infrastructure model serves as a centralized digital register for managing mining infrastructure across both surface and underground operations. We store all infrastructure objects within a single system using geometry, technical parameters, status, and complete lifecycle history. We can link drawing, passports, photos, and documents directly to each object and reference them spatially within the mine layout. Also, we use built-in tools for change tracking, reporting, and data export to make sure that we have control over infrastructure asset. So we can support informed operational and management decisions. So this model allows you to create an integrated 2D and 3D master plan that combines spatial geometry with structured semantic data. You can also represent buildings, facilities, transport and utility networks, terrain elements, and topography within a single, consistent cartographic model. So all of that allows you to follow industry standards and custom specifications. Additionally, you can import infrastructure data from external sources and align it within a unified coordinate system. This ensures spatial consistency across the entire site. So if we talk about object parameters, you can enrich it with technical attributes stored in the centralized database. So this way you can shape a comprehensive digital register of all infrastructure assets. And of course, you can also link infrastructure elements to drawings, documents, and photos, maintain full transparency and lifecycle tracking, and navigate quickly between database records and spatial objects to simplify analysis and control. So as far as the reporting tools, you can use them for basic 3D modeling, reporting, integration with external systems such as ERP platforms, and all this makes the infrastructure model a reliable foundation for infrastructure planning, monitoring, and operational management. That's it. You've done it. If you've been here since the beginning of the presentation, I'm especially proud of you. And if you come into Toronto for PDSC, please stop by our booth. The number is 6625N in the North Building, and our team will be there. We'll also post more detail on our LinkedIn page if you're not coming to Canada but are interested in exploring any of the models described today. Drop us a comment here or reach out to us through our contact form on our website, and I'll see you next time.